Welcome to the lesson on logarithmic functions. So we spent a whole lesson on exponential functions. Log functions are essentially, we'll take a look at what that means. This is a lesson that a lot of these topics we would have covered in Algebra 2 had we not gotten cut short last year. I mean, I know we finished the year out, but we also didn't do as much cover as much material as we would have had we not gone home. So some of this stuff will be newer, so we'll take it slow. A lot of objectives for this one. Let's see. We're up to eight objectives. So we're going to change from logarithmic to exponential form and then back. So there's a way to interchange between the two. We're going to evaluate logarithms, meaning, evaluate means basically you're going to get a number answer. We're going to talk about some properties. We're going to graph them. We're going to talk about domains of them, and then two essentially special cases, the common and the natural logs. So a lot's going into this lesson. Definition of a log function. So for any x value greater than 0, so x has to be greater than 0, and for a b value greater than 0, y equals the log base b of x is equivalent to saying b raised to the power of y equals x. So a log function is just an exponent, an exponential function written in a different form. So the way that you would read this is the base b, all right, has an exponent of y that equals x. So when you say log base b of x, that's equivalent to the exponent that you put on b to get x, okay? So we're going to write each equation in its equivalent exponential form. So if the log statement is 3 equals log base 7 of x, that's the same thing as saying 7 to the power of 3 equals x. And 2 equals log base b of 25 means b raised to the power of 2 equals 25. Then log base 4 of 26 equals y means 4 raised to the power of y equals 26. And then going back again. So next part of the objective is going from exponential to log. So 2 raised to the power of 5 equals x is the same thing as saying 5 equals log base 2 of x. There we go. So essentially, the 5, oh, I don't mean to do that. All right, come on. There must be a better way to do this. Maybe not. There we go. All right, so the 5, that's your exponent, goes here, right? The base here is your base here. And what it's equal to here goes here. And it's the same setup. So b raised to the power of 3 equals 27 is the same thing as saying 3 equals log base b of 27. The 3 goes there, the b goes there, and the 27 goes there. E to the power of y equals 33 is the same thing as saying y equals log base e of 33. There we go. So evaluate. All right. So this is equal to the exponent that you put on 2 to get 16. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's 4 2's you multiply together to get 16. So log base 2 of 16 is equal to 4 because that's the exponent you put on 2 to get 16. Okay. Log base 10 of 100 would evaluate to 2 because the exponent you put on 10 to get 100 is 2. Remember when an exponent is negative, that's when you get the reciprocal. So it's definitely going to be negative. And then 5 turns into 1/24. 5 times 5 is 25 times a third 5 is 125. So if it was log base 5 of 125, that would be 3. The fact that it's 1 over 125 is why it's negative 3. A base can get smaller. So everything we've looked at so far, the base gets bigger, with the exception of this one, but the absolute value or whatever, the denominator is bigger than the base of 5. If it gets smaller, so 36 turns into 6, that's a square root, right? The square root of 36 is 6. The index of that radical is 2, so it's 1/2. If it was a cube root, then it'd be 1/3. If it's a fourth root, it'd be 1/4, and so on. Which is how you're going to handle this one. 3 now turns into the 7th root of 3, so it's 1/7. Some basic log properties now. Log base b of b equals 1 because 1 is the exponent that you put on the base b to have it end up being b. So b to the power of 1 is equal to b. So that's why if the base and what you're taking the log of are the same, it evaluates to 1. If this number is 1, it doesn't matter what the base is. The exponent you put on anything to get 1 is 0. So this one, log base b of 1, would evaluate to 0. It doesn't matter what b is. Let's use those properties. Log base 9 of 9 is going to use that first property we just talked about. Because log base b of b equals 1, we can conclude that log base 9 of 9 equals 1. So log base 3 of 3 is 1, log base 10 of 10 is 1. If those numbers are the same, it evaluates to 1. Evaluate now log base 8 of 1. It's going to equal 0 because it doesn't matter what the base is. If that number is 1, the exponent you put on any base to get 1 is 0. So this is going to evaluate to 0. For b's that are greater than 0 and b's that don't equal 1, log base b raised of b to the power of x is going to equal x. All right. And then if you make that an exponential statement, b raised to the power of log base b of x is equal to x. So using that same property, log base 7 of 7 to the 8th is going to equal 8. So if those numbers are the same, that's going to evaluate to whatever the exponent on that bigger number is. 3 raised to the power of log base 3 of 17 is going to equal 17. But basically the bases cancel out. Now we're going to talk about graphing. First thing is you set up a table. So we're going to graph the exponential function that we talked about in 3.1 and then log base 3 of x. So 3 to the power of x and then log base 3 of x. I'm going to graph on the same table. So we're first going to set up a table for coordinates of the exponential function. So that's what you see over here. And there's your table. We're substituting in 4 numbers, -2, -1, 0, and 1. You substitute -2 in for x, 3 to the power of -2 is 1/9. For -1, 3 to the power of -1 is 1/3. For 0, 3 to the power of 0 is 1. And then for 1, 3 to the power of 1 is 3. Now you're going to reverse those. Because g of x, the log base 3 of x, is the inverse. So if the ordered pairs for the exponential function, the x on the left, the y's on the right, you're just going to flip them. All right, so again, here's your table we just created for the exponential function. -2, 1/9. The exponential function becomes 1/9 -2 for the log function. Again, you just flip the x and the y. Same numbers, just flip the side. when you plot those points, the exponential function looks like this. The log function is in blue. And again, these points are plotted from the tables that we just looked at. All right, characteristics of some log functions. I don't think I left anything for you to write for these, so just sit back and listen for a minute. All right, the domain of f of x equals log base b of x consists of all positive real numbers, 0 to infinity. So x can be 0, right? And it can be positive, but it can't be negative. The range is all real numbers. So like the x could go from 0 to and up, but the y could go up and down. The graphs of all log functions of the form f of x equals log base b of x pass through the point 1, 0. And that's because when x is 1, the whole thing evaluates to 0, like we talked about. So the x-intercept is 1, and there is no y-intercept. It would flatten out before it would cross the y-axis. If b is greater than 1, f of x equals log base b of x has a graph that goes up to the right and is an increasing function. If the b value is between 0 and 1, the graph goes down to the right and is a decreasing function. The graph of f of x equals log base b of x approaches but does not touch the y-axis, just like the exponential function approached but did not touch the x-axis that we looked at last lesson. So then there's a vertical asymptote, just like the exponential function that we looked at last lesson had a horizontal asymptote. All right, domain of a log function. I'm going to dive a little bit more into this. So the domain of an exponential function of the form f of x equals b to the power of x includes all real numbers, and its range is the set of positive real numbers. Right? Because the log function reverses, it's the opposite. The domain of a log function is a set of all positive real numbers. The range is all real numbers. That's the same information that we just showed or talked about on the previous slide. This is important. The argument of a logarithmic function must be greater than 0. So the argument is considered the part that's the x minus 5. So since that must be greater than 0, if you set that equal to 0, you set that greater than 0, and then you solve for x, you get what the domain is for a specific log, right? So when we were saying that x has to be greater than 0, we're talking about just like log base b of x, right? But what if it's something else? What if it's x minus 5? So you just have to solve for that. So if the domain, for instance, was x plus 3, you would say, all right, well, x plus 3, and the 2 doesn't matter for this. We're just looking at this part here, the x plus 3 has to be greater than 0, so that means you subtract 3 and you get x is greater than negative 3. All right, so then your range would be that, negative 3 up to infinity. If it was 2x minus 5, you add the 5, divide by 2, and you would say that 5 halves to infinity is your domain. 3x plus 7, same thing. Subtract 7, divide by 3, and you get negative 7/3 infinity. All right, and then for the last one, it doesn't matter that it's getting squared because it just needs to be x minus 4 needs to be greater than 0. And the way you can think about that is if as long as x minus 4 is positive and you square it, it's going to stay positive, right? So it doesn't matter that there's that exponent there. That's actually meaningless in terms of finding the domain. If x minus 4 is greater than 0, you just have x is greater than 4. So then that means 4, comma, infinity would be the would be the domain. Okay. The logarithmic function with base 10 is called the common log. So if you look on your calculator and you see a log button, it's considered the common log, and the 10 is implied. So the function f of x is equal to log base 10 of x is usually expressed just log of x. So in that case, the 10 is implied. So here's an application. The percentage of adult height attained by a boy who is x years old can be modeled by f of x equals 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has the boy attained at age 10? So what you're going to do is substitute 10 in for x. So they're giving you the function. You're just substituting 10 in for x. So 29 plus 48.8 log 10 plus 1. So now it's 29 plus 48.8 log of 11. So if you were to evaluate that on your calculator, you're using that log button on your calculator. So I mean, literally just type it in as 29 plus 48.8 times log 11. It's implied that it's the base of 10 by when you use that button. So a 10-year-old boy has attained approximately 80% of his adult height. So some general properties. These are the ones we already talked about, right? For a common log, it basically works the same. Log of 1 is still equal to 0 because the exponent you put on 10 to get 1 is still 0. Log of 10 is equal to 1 because the exponent you put on 10 to get 10 is 1. Log of 10 to the power of x is equal to x based on the inverse rule. And 10 raised to the power of log of x is equal to x. Another one we're going to talk about is a natural log. So this is the last part of the objective. So the logarithmic function with base e is called the natural log function. The function f of x is equal to log base e of x is usually expressed f of x equals natural log of x. So a base e, you would just write it as this natural log. So this notation means this. Properties all work kind of the same, right? So natural log of 1 is equal to 0 because the exponent you put on e to get 1 is 0. Natural log of e is equal to 1 because the exponent you put on e to get e is 1. And then the inverse one works the same as well. So when the outside air temperature is anywhere from 72 degrees to 96 degrees, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. So then the function f of x is equal to 13.4 times natural log of x minus 11.6. So that 11.6 is separate. If that 11.6 was part of the log, you'd have parentheses around it. So it's just the x. That's part of the log. That models the temperature increase in degrees Fahrenheit after x minutes. So use the function to find the temperature increase to the nearest degree after 30 minutes. So you're just going to substitute 30 in for x. Again, you're just given the log function. You're substituting 30 in for it and then evaluating. So after 30 minutes, the temperature raised 34 degrees. That's why it's really important not to leave anybody or any pet in a car when the sun's out. There's 34, like think about it, if it was 70 degrees, now it's 104 degrees in your car after just 30 minutes. Anyway, getting a little off topic, but that is what that question is showing you. Give the exit ticket a try, and we will go over this together tomorrow. Let me know if you have any questions.